Now, the concept of the integral in calculus and its relationship to the derivative, and the relationship is going to be that to evaluate integrals, you frequently can do this by finding a function whose derivative is a given one. That's called the antiderivative of the given function, and then looking at the values of that function. Let's take a look at how this goes. If you know the position x times t on the x-axis, let's say s of t or x of t of a given particle, then if you compute the quantity x of t plus delta of t, that's the position at time t plus delta t, subtract x of t, this is the change in position, and divide by delta t, the quantity that you have is the average velocity of, that's to say, the change in position divided by the change in time. Now if you take the limit as delta t is again is just one symbol, it's two symbols representing one thing. Take the limit as delta t approaches 0 of this, you get the derivative, which should be the velocity of the particle at the time t. That's to say, as delta t gets very small, this is very close to the actual velocity at the fixed time t. So that the velocity is the derivative of the position. Now, if you were to take the velocity as times t plus delta t at a slightly different time, subtract the velocity as t and divide by delta t, this would be the change in velocity across the time interval delta t, and this is going to represent the average acceleration. Now, if you take the limit as delta t approaches 0, then this is going to be the acceleration, but it's also clearly going to be the second derivative, x double prime of t, of the position function. So that we get the acceleration is the derivative of the velocity, which is the second derivative of the position function. Right. In general, of course, here, if you've got a function f of t, the derivative represents the rate instantaneously of the change in f with respect to t. Now, the situation is this. If you knew the acceleration of a particle, or if you knew the velocity at every time t, you'd expect to be able to go backwards. If you knew the velocity at time t, you'd expect to be able to go backwards and find out what the position was at any given time t, if you knew where the particle started. And similarly, if you knew the acceleration at any time t, you'd expect to be able to find its velocity at any time t if you knew its velocity at some fixed original time. Right? That's to say, you'd expect to be able to take the acceleration function and find a function whose derivative was it. Now, we're going to find out just shortly here that the antiderivative, or a function whose derivative is a given one, is not unique, but it is nonetheless unique up to a constant. It's kind of clear pictorially here that if we have two functions, capital F and capital G, and they differ by a constant, then they're going to have the same derivative. The converse actually is the case also, that if you've got two differentiable functions that have the same derivative, then the one is just the other one with a constant added on. So here, for example, let's take a look at an illustration. Let's suppose that we know that acceleration at time t is equal to t plus 1. All right. Then, the velocity at any time t should be an antiderivative, a function whose derivative is t plus 1. Well, one such function is going to be t squared over 2 plus t, because the derivative of this is going to be t plus 1. And the general function that's going to have t plus 1 as its derivative is t squared plus over 2 plus t plus any constants. So, knowing the acceleration at any time t would give us the velocity with it a constant. Right? Now, if we do the velocity at time 0, let's suppose, for example, that the velocity at time 0 was equal to 3, then v of 0, if we put 0 in here, we get c on this side here. Right? It's not always the case that putting a number over here is going to give you the number c, but in this case it does. So then we know that c is equal to 3, and so the general velocity here at any time t would be t squared over 2 plus t plus 3. This confirming the idea that if we knew the acceleration, we should be able to find out the velocity. If we just knew, let's say, the initial velocity at a particular time, in this case 0. Now, if we know the velocity, we should be able to find the position at any time. If we know the position at a fixed given time. So that, for example, here, a function s of t, whose derivative is v of t, is given by t cubed over 6 plus t squared over 2 plus 3t, because the derivative of this is going to be t squared over 2 plus t plus 3. And now if we add a second constant out here, d, let's say, then any function whose derivative is this is given by t cubed over 6 plus t squared over 3, t squared over 2 plus 3t plus d. And now if we knew, for example, the position at time 0, let's suppose that this particle started at the point 4 at time 0, then since s of 0, when you put 0 in here, you find out that it's equal to d. We then have that d is 4 and s of t is equal to t cubed over 6 plus t squared over 2 plus 3t plus 4. And so we found out the position of the particle at the time t. Now, if you've got any function f of t, right, the function capital F of t is going to be a function whose derivative is little f of t, and to go backwards, this is symbolized as follows. This is an elongated f. You put f of t in here like so, and you follow it by the symbol dt. Now there's rationale behind this, but not complete. However, the rationale is complete enough so that it makes sense to use this perhaps cumbersome-looking symbolism here for the antiderivative. That's to say, if f prime of t is little f of t, then capital F of t is antiderivative of little f of t with respect to t. That's how this is read, the antiderivative of f of t with respect to t. And antiderivatives are not unique, but they are up to an additive constant. So that if you write antiderivative of little f of t with respect to t like so, then it's normal to add on a constant, or to write that the antiderivative of a function little f of t with respect to t is equal to a given function f of t plus any constant, because these will have the same derivative as capital F of t, namely little f of t. Right. We're going to want to see that the antiderivative is unique except up to constants, and determine how to use them. Okay, we want now to see that two functions have the same derivative and they differ by a constant. So suppose f prime of x exists and it's equal to g prime of x on an interval AB. All right, and then we want you to conclude f of x is g of x plus a constant. Well, if f prime of x is g of x on AB, then if we let h of x be equal to f of x minus g of x, then we need to show that h of x is a constant. All right. So suppose that h of x is not a constant. If h of x is not identically constant, then there are 2 points, x1 and x2, in the interval AB, so that h of x1 is not the same as h of x2. Right. Then, by the mean value theorem, for differentiable functions, h is differentiable, and we know for that matter, h prime of x is equal to 0 on AB, but by the mean value theorem, h of x1 minus h of x2 over x1 minus x2, which is not equal to 0, is equal to the derivative of h at some point z, where z is in the open interval x1, x2. If x1 is less than x2, huh? But this is a contradiction. This can't possibly be here, because this is not equal to 0, and this is. So it then follows that if h prime of x is 0 on an interval, then h is a constant. The only possible functions that could have a derivative of 0 are constants, and so consequently, if the derivative of f is the derivative of g, then f differs by a constant from g. F is equal to g plus a constant. So this justifies that using this, when you find an antiderivative, it justifies writing that the general antiderivative is f of x plus a c, constant c, where f of x is any antiderivative of the function little f of x. Okay, now we're going to want to know how to find the antiderivative of a function or given the function. That's to say, given a function f of x, we're going to want to be able to find a function capital F of x. So if the derivative of capital F is little f. In general, there's no easy process for doing this. In fact, in general, there's no process for doing this. And unlike derivatives, antiderivatives do not obey a lot of rules. There are really only 2 rules that you can count on with respect to antiderivatives that are algebraic in character. The first of these is as follows. If we take a constant times a function, the antiderivative of a constant times a function is a constant times the antiderivative of the function. This is because, of course, the derivative of a constant times a function is constant times the derivative of a function. And the second of the rules is the antiderivative of the sum of 2 functions is the sum of the 2 antiderivatives, providing both of the functions have got antiderivatives. And this, of course, is again because the derivative of the sum of 2 functions is the sum of the derivatives. And so that if we had this function here whose derivative was f, and this one whose derivative was g, then the derivative of the sum of them would be f plus g. Okay. In either of these cases here, you can add on the constant, which is called the constant of integration, to indicate that any real solution to this differs from any other one by a constant. Now we're going to want at least to know some basic antiderivatives of functions that we're familiar with. And first of all, we're going to want to know the antiderivative of the function x to the nth power with respect to x. And a good guess here might be x to the n plus 1, or a reasonable first guess at any rate. The derivative of x to the n plus 1 is equal to n plus 1 times x to the n. So that's not right. However, since the antiderivative of a constant times a function is the constant times the antiderivative of the function, if I divided this by n plus 1, then the result would give me n plus 1 x to the n plus 1 over n plus 1, or x to the n. So here's a specific antiderivative of x to the n, and any general one then differs from this by a constant. So the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus any constant. This is also going to be true here if we replace the n with the rational number r, and providing r is not equal to minus 1. The antiderivative of x to the r power is going to be x to the r plus 1 over r plus 1. And as a consequence of that, and these two rules here, one can now find antiderivatives of anything that looks sort of like a polynomial. That's to say, if it looks like constant multiples of powers of x, and sums of those. So that, for example, x to the 7th plus 3x to the 5th minus 4x cubed plus 2x to the 1/2 minus 10 x plus x to the minus 1/4 plus 11. If we want to find the antiderivative of this with respect to x, we'll symbolize this like so. And now, because this is a sum, we can take the antiderivatives of the individual elements. The antiderivative of x to the 7th is going to be x to the 8th over 8. You take the antiderivative, you raise it to the next highest power and divide by that highest power. And this is 3 times x to the 5th, so the antiderivative is going to be 3 times the antiderivative of x to the 5th, or 3x to the 6th over 6. Antiderivative of x to the 5th, x to the 6th over 6. Now, minus 4, x to the 4th over 4, minus 4 times the antiderivative of x cubed, and the antiderivative of x cubed is going to be x to the 4th, 1 higher power, divided by the higher power, plus 2, x to the 3/2 over 3/2, minus 10, this is x to the 1, so the antiderivative is going to be x to the 2 over 2, plus what? This is x to the minus 1/4, so if we raise that by 1, we're going to get x to the 3/4, divided by the higher power, 3/4, plus 11. Now this is x to the 0 here. The antiderivative of x to the 0 is going to be x to the 1. That's to say, a specific case of this is that the antiderivative of x, of a constant, is equal to a constant times x, and then plus a constant. So here that is the general antiderivative of this particular polynomial-like function. Okay. So at this point here, we could find an antiderivative for things that look like polynomials. There are also, just due to the functions that we know how to differentiate, there are several other formulas that we can write here for antiderivatives. In particular, the antiderivative of sine of x with respect to x is going to be minus the cosine of x plus any constant. And the antiderivative of the cosine of x with respect to x is going to be equal to the sine of x plus any constant. And there are clearly a couple of others that we could write here. The antiderivative of the secant squared. Since the derivative of the tangent is the secant squared, the antiderivative of the secant squared will be the tangent. Right? Similarly, secant times tangent is the derivative of secant. So consequently, the antiderivative of secant times tangent will be the secant. So here we have the ability, at least right now, to find antiderivatives of polynomial-like things here, that's to say multiples of x to a particular power, and also of a couple of other functions because we already know how to differentiate. Let's take now a look at an example of a strictly anti-differentiation type problem. The situation here is this, that near the surface of the Earth, the acceleration due to gravity is a constant, and that constant is written as g, and in the English system this is 32 feet per second squared in the downward direction. If we now imagine, let's say that an object is thrown with an initial velocity, say of 80 feet per second, from a height, let's say, position at time 0 of 4 feet. Right. We then wish to know a number of things frequently with respect to this object, this type of problem. Namely, how high does it go? When does it hit the ground? And how fast is it going when it hits the ground? So what we wish to do here is to find the velocity at any time t and the position at any time t. And when we know those, then these will allow us to determine how high it goes and when it hits the ground and how long it takes for it to reach its peak and questions of this nature. So what do we have here? We have S double prime of t, or A of t, is equals to minus 32. The acceleration is in the downward direction, so minus 32. So consequently, S prime of t, or V of t, is going to be an antiderivative of this with respect to t, minus 32 to t, plus a constant. But now, since we know V of 0 is 80, that means C is 80. So that V of t is equal to minus 32 to t plus 80. Now, this is S prime of t. So from this we can find out what S of t is. It's going to be equal to minus 32 t squared over 2 plus 80t plus another constant. And we know that S of 0 is 4, and S of 0 from this is equal to b, so that consequently S of t is equal to minus 16t squared plus 80t plus 4. Okay. Now, it's going to reach its peak when the velocity is maximal. I'm sorry, when the position is maximal. That's to say when the velocity is 0. The velocity here is equal to 0 when, 80 is equal to 32 to t, or when t is equal to 2.5. So this is the peak. So if you want now to know how far it goes, S of 2.5 is the maximum height that it attains. We just simply take S of t here, we put 2.5 in here, so this is going to be equal to minus 16 times 5 halves squared plus 80 times 5 halves plus 4 in feet. Now the maximum height is attained then. If it's the ground, what S of t is equal to 0. S of t is equal to 0 when what? This is 0, that's to say when t is equal to minus 80 plus or minus the square root of 80 squared minus 4 times 16 times 4 times minus 16 times 4, so this is plus 16 squared over minus 2 times 16. Right. Here, t is going to be positive when it hits the ground, so that the quantity that has all of the negative signs in here is going to represent t. So this is t when it hits the ground. Now if you want to, this is t, if you want sub 1 here when it hits the ground. And if you want to know how fast it's going when it hits the ground, you want to compute the velocity at the time t sub 1. That's to say you take this number here, you put it in the formula for v of t, minus 32t plus 80, and you arrive at the number which gives you in feet per second the velocity of this object when it hits the ground. So here's an example, a strictly anti-differentiation example, whereby you can find the position of a thrown object with a known velocity and initial height at any time t. All right, we now want to look at anti-differentiation method, which is known as anti-differentiation by substitution or integration by substitution. It's based on the chain rule. You know that the derivative of f of g of x is the derivative of f at g of x times the derivative of g at x. So the antiderivative of this with respect to x is going to be equals to f of g of x plus any constant. All right. Now, the problem, of course, is that it's not easy to recognize f prime of g of x times g prime of x as something that, if you're dealing with something, it's not easy to recognize that it's of this form here. And this is going to illustrate part of the reason why this notation with the dx is used. Okay, the idea behind substitution is this. Suppose we let u be g of x in the quantity that we wish to integrate or anti-differentiates. And then du dx will be g prime of x, or in differential notation, du is g prime of x dx. And now the question is, could we change this here by putting u in for g, and where we see g prime of x dx, put du. So the question then is this equal to the antiderivative of f prime of u, putting u in for g of x, times g prime of x dx, we're going to substitute with du. And what? The antiderivative of f prime of u with respect to u, right? Now here we're anti-differentiating with respect to a different variable, and this always tells you the variable that's involved. The antiderivative of f prime of u with respect to u is going to be the function f itself, at u plus any constant. But now u was g, so this is f of g of x plus any constants. And now here we find that we've got f of g of x plus any constant if we do this directly like so. We've also got f of g of x plus any constant if we make this substitution and carefully also changing the g prime of x dx to du, and then anti-differentiate and substitute back. And so that removes this question mark here. That's to say, you can anti-differentiate this right here. If you make the substitution, u equals g of x, and complete the substitution so that everything is in terms of u, letting du be g prime of x dx. Then, if you do that, you may anti-differentiate, and you will end up, when you substitute back again, u equals g of x, you will end up with the correct answer. So this is the method of anti-differentiation by substitution, and we'll look at some specific examples of it next. Okay, now for some specific examples, the anti-differentiation by substitution. Let's look at suppose we wish to find the antiderivative of x sine of x squared with respect to x. Right. Here, we're going to let u equal x squared. There are generally only a few things to try here, and as you work with them, it becomes clear that what one should perhaps try first. Let's let u equal x squared, and then du dx is 2x, so that du is 2x dx. And then this becomes then, when we make the substitution, sine of u, since u was x squared, and now 2x dx is what we should have here. We can correct this by putting it to 2 here, and then and a half on the outside, and that will keep the result the same. Or we can write x dx is du, so that's these du over to 2, so that's 1/2 sine u du is the required quantity over here on this side. And now the antiderivative of the sine is minus the cosine, so that we're going to get that this is equals to minus cosine of u plus any constants. And now u was x squared, so minus cosine of x squared plus any constants will give you the antiderivative. Now, here as elsewhere, a good guess sometimes is just as good a method as any. That's to say, if you had guessed cosine of x squared and differentiate it, you find that the derivative of the cosine of x squared is minus the sine of x squared times 2x. Well, you're off by a factor of minus 2. And whenever you're just off by a constant multiple, you can then fix this by correcting by that multiple, so that minus 1/2 cosine of x squared will then have, for its derivative, the minus 1/2 will cancel here, and we'll get sine of x squared times x. And so if you guess and you can get within a constant multiple of the correct answer, you can get the correct answer by making the appropriate correction. Okay, let's look at a second one here. The antiderivative of square root 3x plus 1 with respect to x. Here let's let u equal 3x plus 1. That's what we would like to get rid of. And then du is equal to 3 dx. That's to say du dx is 3, or in differential notation, du is 3 dx. So this then becomes the antiderivative of the square root of u. Here again we want to write this in exponential form here. And what? Dx is du over 3, so 1/3 u to the 1/2 du. The antiderivative of this is going to be 1/3. To anti-differentiate u to the 1/2, we raise it to 1 higher power, 3/2 divided by 3/2 plus any constant. And now u was 3x plus 1. So 3x plus 1, 1/3, 3x plus 1 to the 3/2 over 3/2 plus a constant. Of course, you can simplify that. both this and the previous case are ones where you could perhaps make a good guess. That's to say, if you were to guess here, 3x plus 1 to the 3/2 power and differentiate it, you find the derivative is 3/2 3x plus 1 to the 1/2 times 3. Right? This is just off by a constant multiple of what you want, and so you can correct it by multiplying by the appropriate constant. Okay, let's take a look at another one here. Let's take a look at the antiderivative of x squared times the square root of x plus 7. All right. Here, I don't like to see the square root of x plus 7 in this problem, so I want to get rid of it. I want to let u equal x plus 7. Right? du is equal to dx. Right? And then this becomes antiderivative of square root of u. Du is dx. But now, how do I get rid of the x squared here? This really has to be changed over completely in terms of u. Well, if u is x plus 7, then x is u minus 7, and x squared is u minus 7 squared. So what belongs in here is u minus 7 quantity squared. Right? We now have then that this is equal to antiderivative of u squared minus 14u plus 49 times the square root of u du. Okay. And here, when you've got something that can be put into polynomial form, frequently that's the only way in which you can do anything with it. That's to say, if we put it into this following form here. If this is u to the 1/2 and I multiply this out, this becomes u to the 5/2 minus 14, this is u to the 1 times u to the 1/2, u to the 3/2 plus 49 u to the 1/2 du. And now an antiderivative of this is going to be u to the 7/2 over 7/2 minus 14u to the 5/2 over 5/2 plus 49u to the 3/2 over 3/2, and you now substitute back u equals x plus 7, and you have the solutions to this problem right here. Using substitution now, it's possible to get slightly improved formulas and to be able to recognize sometimes when you can find the antiderivative of a function real easily. In particular here, for example, instead of just the antiderivative of x to the nth power, if we looked at f of x to the n power, right, times f prime of x, this is going to have for its antiderivative f of x to the n plus 1 over n plus 1 plus any constant. And that's perhaps worth noting. You could either get it by differentiating this and finding that you get f of x to the n times f prime of x. And this actually holds for all n except for minus 1, where of course it doesn't make sense. You can differentiate this to get this, or you can get this formula here also by using the substitution u equal f of x. And then you're going to have antiderivative of u to the n du, where u equals f of x, and f prime of x dx is du. And this is going to be u to the n du, which is u to the n plus 1 over n plus 1 plus any constant, and that gives you f of x to the n plus 1 over n plus 1 plus any constants. So that if you can recognize that you're dealing with a function to a power times its derivative, where the power is not minus 1, then you can immediately find the antiderivative of it. So that, for example, if we wanted x times x squared plus 7 to the 30th power. All right, well now, this is a polynomial and we could multiply it out. But it's clear that this function here is raised to a power. We've almost got the derivative of it in the front here. If we had 2x in front, we would have the derivative. If we multiply by 2 here and a half on the outside, which was illegitimate because the antiderivative of constant times the function of constant times the antiderivative of a function. And it's one of the few legitimate things to do here. All right. Then we recognize that we've got f prime of x to a power. So the antiderivative of this is going to be the half stays here. We've got then f of x squared plus 7 to the next higher power, 31st power over 31 plus any constants. Okay? So if you can recognize that you've got a function times its derivative, function being raised to a power, then you can anti-differentiate it. Substitution will always work here also. If we were to let u equal x squared plus 7, then du is going to be equals to 2x dx, and this is going to be equals to the antiderivative of, 1 half 2x dx is du, u to the 30th, du, which is going to be u to the 31st over 31 times a half, and u was x squared plus 7, so that the substitution here will always work also to give you the antiderivative. Right. In some cases, your best bet is to just multiply things out. That's to say, if you had something like x squared times x plus 1 squared, and you want the antiderivative of this with respect to x, substituting around here is not going to get you anything. You're not looking at f prime of x to a power. Your best bet with this is to just write this, multiplying the x plus 1 squared out. You're going to get x squared times x squared is x to the 4th plus 2x cubed plus x squared dx. And so the antiderivative can be gotten directly here. It's going to be equal to x to the 5th over 5 plus 2x to the 4th over 4 plus x cubed over 3 plus any constant. So sometimes you're just, and sometimes it may even be a large polynomial, but you're just stuck with multiplying things out. Two additional formulas besides this are frequently worth noting. One of them is that the antiderivative of sine f of x times f prime of x dx is equal to minus the cosine of f of x. And the second one is that the antiderivative of cosine of f of x times f prime of x dx is equal to the sine of f of x plus any constant. And again, you can get this either by noting that the derivative of this is this, or by using the substitution u equal f of x, du is f prime of x dx. And so then we're looking at sine of u, and the derivative is going to be minus cosine of u. Similarly here, if u is equal to f of x, du is f prime of x dx, and we're looking at cosine of u. The antiderivative is going to be the sine of u. All right? So if you can recognize that you're dealing with a sine of a function, or the cosine of a function, times its derivative, you can immediately write down the antiderivative of the resulting quantity. Next thing that we're going to be looking at is the integral. This is a motivation for the idea of the integral. Basically, if you've got a function on an interval from a to b, and the function is non-negative, and the geometrical idea behind the integral is that it is the area under the graph of the function between a and b. And A way to get that is to take the interval and divide it up into little pieces like so. That's called partitioning it. And draw small rectangles here by choosing a point in each one of these intervals. Draw some rectangles here so that there's a point here and the height of the rectangle is like so. And you can put this picture here. And if you add up the areas of the rectangles, it's going to be approximately the area underneath the graph. And now if we were to let the size of these rectangles, the width of them, get smaller and smaller, this is going to approach the area underneath the graph. And that's the way in which the integral is going to be defined as a limit of sums of rectangles like this. However, the integral frequently also involves an antiderivative, and there's a way in which you can see how this was originally thought of, that the area underneath the graph here ought to be related to the antiderivative of this function. Let's consider this to be a time axis here, and let's consider that what we're graphing here is a velocity, v of t. Right. Then, what? If we wanted to know now the distance traveled between time A and B, right, it's going to be equal to S of B minus S of A. That's to say we would find the antiderivative of V, and we would take its value at B and subtract the value at A. Another way in which you could do this, though, is as follows. You could say that this was approximately equal to, see, the velocity in each one of these intervals is approximately fixed. And so that if we were to take the velocity in the first interval here, let's say at some point t1 in the first interval, and multiply it by the change in time across the interval, this would be approximately the distance traveled. And then if we were to add to this v at t2, the velocity at a time in the second interval, times the distance, the change in time across that interval, this would be approximately the distance traveled. And so forth here. If we continue to do this, if this was the nth interval, we took the velocity at tn times delta t. Actually, these could be different sized here, so this could be delta t1, delta t2, delta tn. This would be the distance traveled across that little interval approximately. And so this is going to be approximately equal to this. But this is approximately the area underneath the graph, and if we let this get very small, this is going to be, the approximation is going to get more and more accurate. This is approximately equals to here, equals to the area under the graph. So that the area underneath the graph of the velocity function is the distance traveled between the two times a and b when the velocity is positive. All right. The symbol for this area underneath the graph here is going to be the symbol for the integral, and it's going to be written like this: the antiderivative symbol or integral symbol, and then we've got here v of t, and then with respect to t, the only difference is that the two endpoints a and b are put in their respective orders here at the bottom and the top of the integral symbol. This is an elongated s. The idea is that it comes from a sum, and it's the limit of a sequence or of a collection of sums. And it's clear here then that if we wanted to find the area underneath the function b of t, intuitively at least, we ought to be able to take an antiderivative for it and evaluate it at its two endpoints. That's to say, take the value at b and subtract the value at a. Right? So that s of b minus s of a ought to give us that integral. Well, we want to take a look at the theory behind this closer. It ought to give us that area. We want to look at the theory. We want to look at what happens if you take these sums here and take the limit of the sums as the division or partition of this integral gets finer and finer. All right, we want then to look at how to sum up a collection of numbers. And the notation for this is called summation notation or sigma notation. And if you want us to write a1 plus a2 plus a3 plus, and this is to continue on till you get to an, this is written in shorthand as the Greek letter capital sigma. We now let I equal 1 through n, and we add up the ai's. That's to say, when I equal 1, this gives us a1. I equal 2, it gives us a2. Add that on. Keep adding here until we get up to I equal n. Sometimes I equals n is written up here on top to indicate that is what is being done. So this is the brief notation and to indicate that you wish to add up numbers which are indexed by the natural numbers going from 1 through n. If we wanted to go from 3 to n, then we would write I equals 3 to n. Or if we wanted to go from 3 to 5, you would write I equals 3 to I equals 5. Right. Because of addition, there are two rules that summation notation obeys. The first one is this. The summation of a constant times ai, where I goes from 1 through n, is equal to the constant times the sum of the ai, I going from 1 through n. And that's simply because if we have a constant times this, we can factor. We can multiply it out and get c times the ai. That's the constant times the sum of the ai. It's the distributive law. The second is this. The summation of quantities ai plus bi, when I starts at 1 and goes up to n, is what you get if you added up the ai first, sum of the ai, plus the sum of the bi. These are really the two basic algebra rules for summation notation. There aren't really any others. Okay, and to use this, it's worthwhile to note a couple of additional things here. That's to say, have a couple of formulas to tell you what happens when you add up particular types of numbers. If we add up ones from I equals 1 to n, this is going to be what? This is going to be 1 plus 1 plus 1 plus 1. There are n of these. So that this is going to be equal to n. All right? The sum of ones is n. If we take the sum of the natural numbers I going from 1 through n, this is going to be equal to 1 plus 2 plus 3 plus 4 plus till we get up to n. And a formula for this is that this is equal to n times n plus 1 over 2. So this, for example, here is equal to 1 plus 1 plus 1. Right. And it's worth knowing this and this, and a third formula here, which is the formula for the sum of the first n squares. The sum I equals 1 through n of I squared is equals to n times n plus 1 times 2n plus 1 divided by 6. This is 1 plus 4 plus 9 plus, and so forth here, until you get up to n squared. Now, you can see that this is the case immediately here. You can show that this is the case, or this is the case by induction. I'm not going to go into the details of that. Here, there are actually formulas for the sum of the integers to the kth power from I equals 1 through n. So here are some basic basic things about summation. This is the notation. Those are the two basic algebra rules. And here are three things here that, three formulas that are worth knowing. Okay, we're now going to do something that's traditional at this point. That's to say we're going to compute an area using summation and see how this works. In particular, let's take a look at the function y equals x squared between 0 and 1. And let's compute what this area in here between 0 and 1 is underneath the graph of y equals x squared. And to do this, what we're going to do is we're going to imagine that we divide this up into n equal parts here. So this is going to be 0, then 1 over n, 2 over n, 3 over n, and so forth here. The last part is 1, which is 1 n over n. Right. And we're going to form then rectangles here. We'll form ones that are just a little bit too large. Let's take the right-hand end point here and form these rectangles and use them to approximate the area underneath the graph, and then let n get very large so that our approximation will be more and more accurate. This will always give us, this particular approximation will clearly always give us an approximation which is too large. Right? What happens here then? Well, if we look at the ith rectangle, right? It has height I squared. The first one is, I over n squared. So I squared over n squared. The first one is 1 over n, and it's got height 1 over n squared. Second one, 2 over n. The ith one is going to be have height I over n. And so the nth one is going to have its right endpoint I over n, and so the height is going to be I over n quantity squared. And the width of each of these is 1 over n. So in terms of summation notation, if we take I over n squared times 1 over n, right, what we wish to do is we wish to add these up, I going from 1 through n. And then this will be approximately the area. This quantity, well, here. So this is going to be equal to the sum, I equals 1 through n, I squared over n cubed. Now, 1 over n cubed doesn't have, is a fixed number with respect to this sum here, n being fixed. So we're going to have 1 over n cubed, the sum of the first n squares. Right? And this is going to be equal to 1 over n cubed. Recall that the sum of the first n squareds is n times n plus 1 times 2n plus 1 over 6. So this is going to be equal to what? We've got 2n cubed, multiplying this out, 2n plus 1 times n plus 1 is 2n squared plus 3n plus 1, so that we're going to get 2n cubed plus 3n squared plus n over 6n cubed. That's going to give you a formula of the approximate area underneath here. Now, if n is very large, you can treat this just like as if it was x, so that if x was very large, this is going to approach 2 over 6. Right? If you like dividing numerator and denominator by n cubed, we have 2 plus 3 over n plus 1 over n squared divided by 6, and as n gets very large, this and this are small, and the resulting quantity is close to 2 over 6, or 1/3. Okay? So the area underneath here you expect is going to be a third. All right. You could do the same type of calculation using smaller rectangles and show that it's got to be larger for the third, and so the area has to be exactly equal to a third. Now, in terms of antiderivatives, all right, as was mentioned before, if we could find an antiderivative of this, of x squared with respect to x, which we can, of course, it's going to be x cubed over 3. And now if we take that antiderivative and take its value at 1 and subtract its value at 0, we're going to have then the integral of this function, or the area underneath the graph, since the function is non-negative. It's written as the integral from 0 to 1, and to do that we wish to evaluate this at 1 and then subtract the value at 0. That's abbreviated by putting a 0 down here and a 1 up here. This means take the value at 1 and subtract the value at 0. So this is going to be equal to a third minus 0, or a third. So finding an antiderivative for x squared here and taking the value at the two endpoints, subtracting one from the other, gives you the area underneath the graph, and it clearly does it a lot easier than this when it's possible to find such an antiderivative. We don't want to get precise about the matter. We want to give a definition for the integral, or the Riemann integral, of a given function. The exact definition here is attributed to Riemann, who worked on the idea of taking these, taking a function f of x on an interval a, b, and partitioning the interval like so. So a partition P is going to be a collection x0, which is A, x1, x2, up through xn, which is B, with each one of these less than the next. The general elements in here are going to be the I minus first and the ith. Okay. In order to find the integral here, we're going to want to add up the values of these rectangles, like so. The illustration here is for f of x greater than 0. However, the definition will then just be used in the case that f of x is less than 0, and appropriate interpretation will be given. Right? If we've got a general interval xi minus 1 to xi, then delta xi is the width of that interval. It's xi minus 1. So if you like, this is the change in x, the ith change in x. It's xi minus 1. Now, what you want to do here is you want to choose a point wi in the interval xi minus 1 to xi. It could be either of the endpoints or any point in between. And then you form the sum f of wi delta xi. This is the height of the rectangle here, and this is the width. You multiply these together here, and you sum this up, I equals 1 through n. All right? And then what we want to do here is we wish to take the limit here, the limiting value here, as the norm of a partition goes to 0, where the norm of the partition is equal to the maximum value of the delta xi's. It's the length, it's the width of the widest interval in the partition. We want to do this, and this is going to be the definition, a definition of the integral from a to b of f of x with respect to x. It's equal to this limit here. Now we need to say what this is. I mean, if we've got a partition, we can form a particular sum here. We need to say what the limit is. Where So where the limit as the norm of the partition goes to 0 of the sums f of wi delta xi, I equal to 1 through n when there's n elements in the partition. This is equal to L if, right? And now we're going to need epsilons and deltas here to say what it means for this to get as close as you like to L, and so that the limit would be equal to L. So if, given epsilon greater than 0, there is a delta greater than 0, so that this sum, f of wi delta xi minus L, an absolute value is less than epsilon whenever the norm of the partition is less than delta. So that's to say, if the partition is chosen delta small, or small enough, then the difference between any one sum and any other sum at L is going to always be less than epsilon. Between any sum with a partition is fine enough, the sum of these values, f of wi delta xi, will differ from L by less than a number epsilon. And that given any epsilon, no matter how small, you could find a delta for which that is true. Right? So now this is clearly very theoretical definition, but it's one that is somewhat complex and worth memorizing, because you're not going to be able to understand it if you do not have this memorized. Namely, that this is the definition of the integral, the Riemann integral. Okay, we want to look at some properties of the integral of a function f of x, and also properties of the function if it's integrable. I guess the first thing to note there is this, that if integral from a to b of f of x with respect to x exists, that's to say if there's a number, it's the limit of the Riemann sums, then f of x is bounded on the interval AB. This is basically because if the function were not bounded on the interval from A to B, if it took on arbitrarily large values or arbitrarily large negative values, then no matter what partition you chose here, there would have to be one of these intervals in which it took on arbitrarily large values. You could then choose a point wi in that interval to make the Riemann sum be as large as you wanted, and so it couldn't possibly approach a limit. Okay, so if the integral exists, then the function has to be bounded. Also, if f of x is between m and little m on AB, then the integral from a to b of f of x with respect to x is between m times b minus a, so this is then, and little m times b minus a. It's strictly between those two. So that if our function here were between little m and capital M, then what? The integral would be no larger than m times b minus a and no smaller than little m times b minus a. And that's because every Riemann sum would be between little m times b minus a and capital M times b minus a. Okay. if f is not strictly positive, or if f is not negative, the integral from a to b of f of x with respect to x is still defined to be the limit, if it exists, as the norm of the partition goes to 0, of these sums, f of wy delta xi, I equals 1 through n, whether f is positive or negative. If f happens to be negative on a, b, if it's partly positive and partly negative, then when you form a partition sum, delta xi is going to be positive if we go from a to b. F of wy is going to be negative, and what the integral is going to do is it's going to count this area here underneath the positive part of the function as positive, and it's going to count this part right here as negative, where the function is negative. So that the resulting sum, partition sum, is approximately going to be this area here subtracted from this positive one here. All right? So that the integral then is not going to represent area specifically. It's going to represent the area under the part that's above the graph minus the area under the part that's above the x-axis minus the area of the part that's between the x-axis and above the function. That's to say, the negative part of the function here is going to be counted as negative, and the positive is positive. This is worthwhile in a sense. If you were thinking of this as charging some sort of a battery, for example, the positive part would be where charge was going in, the negative would be where it was coming out. If you're thinking of this as some sort of a velocity, the positive part here would be where the velocity was in the forward direction, the negative part would be where it's in the backwards direction. The distance traveled is going to be given still by this integral if there's forward and backwards motion. At any rate, this is the definition of the integral, whether or not f is positive or negative. So when it's positive, you have a simple interpretation as the area above the x-axis underneath the graph between a and b. When it's negative, you have to be more careful. Right? If there's any doubt about it, it's going to be understood that if we integrate a function f of x between a and a, that we get 0. Right? And also, it's going to be understood that if b is larger than a, and we want to write the integral from b to a of f of x with respect to x, that would mean that we would sum this way, so to speak. All the delta xi's would be negative, and so that this, naturally enough, should be equal to the negative of the integral from a to b of f of x with respect to x. Right. So if we go the backwards direction here, then the integral from b to a is going to be the negative of the integral from a to b. Right. Two properties of integrals follow almost immediately from the corresponding properties of sums. That's to say, the integral of a constant times f of x from a to b is constant times integral from a to b f of x with respect to x, and the integral from a to b of f of x with respect to x, of f of x plus g of x with respect to x is equal to the integral from a to b of f of x plus the integral from a to b of g of x. Right? This is because the Riemann sum that you get for this is these two Riemann sums added together. Right? Now this is, of course, this is provided that these two are integrable. If both f and g are integrable, then f plus g is, and the integral is equal, like so. A final property is as follows. Right? Again, I'm going to state this one without going into details on it, but if you've got f integrable on interval a to b, then if we take any point c between a and b, then it's also integrable from a to c. And the integral from a to c of f plus the integral from c to b of f is the integral from a to b of f. All right? So that the integral from a to b can be gotten by taking first the integral to any point c in between and then taking the integral from c to b. So here then are some properties of integrable functions and of the integral. Okay, we now want to look at what's called the fundamental theorem of calculus. This is the theorem that relates the integral and the derivative precisely, and I'm going to just basically sketch what happens here. That is as follows. If we've got a and b here, and a function f of x, I'll draw it as positive for the moment here. Right? Then if f of x is integrable, that's to say if there is an integral of f of x on the interval from a to b, then we can integrate f of x from a up to x. And if we do that, we're going to let capital F of x be the integral from a to x of, now I'm going to change the x inside here to a different letter, f of t each t. Right? Integrating f of t with respect to t is the same as integrating f of x with respect to x, or f of u with respect to u. And in fact, this letter here that occurs underneath the integral sign is sometimes called a dummy variable because you can change it to any letter that you wish. Right? And the reason for doing this is that I want this to be the function f defined at x. So f of x then, if little f was positive, is going to represent the area between a and x. Right? Now we already know that little f, in order for f to be integrable, right, this implies that little f is bounded. Right. Now, with that in mind, we want first of all to see that capital F is continuous. That's to say we want to look at the limits as x approaches x naught of f of x and show that this is equals to f of x naught. Or if you like, that if we take this minus f of x naught, that it's equal to 0. So we want to show that this limit is equal to 0, or that, which will show that capital F is continuous. I'm going to just let x naught be a point here, and let's let x be to the right of x naught and look at the limit from the right here. The limit from the left is similar. All right? This limit right here is equals to show it's equal to 0, we're going to compute what it is. This is the integral from a to x of f of t minus the integral from a to x naught f of t dt. Right? And now this is going to be equal to the integral from x naught to x Right? If I integrate from a to x naught and add the integral from x naught to x, that's going to give you the integral from a to x. So that this is going to be a to x naught plus x naught to x is going to be a to x. So this is equal to this. We want to know what this limit is. This limit. Right? And then this is, to show that this is equal to 0, we can look at the absolute value of it. So let's look at the absolute value of this. And that's the absolute value of this. And now this is going to be the absolute value of this is going to be less than or equals to the integral from x naught to x of absolute f of t dt. Why? Because f of t is less than or equal to absolute f of t, and so the integral of f of t is less than or equal to integral absolute f of t. And in general, if you've got two functions, f of t less than or equal to g of t, then it's clear that from the Riemann sums that the integral of f of t with respect to t is less than or equal to the integral of g of t with respect to t. All right? So that's what? The integral of f of t is less than or equal to the integral of absolute f of t. The integral of minus f of t is less than or equal to the integral of absolute f of t. And so the integral of absolute value f of t, absolute value of the integral of f of t is less than or equal to the integral of absolute f of t. So this limit here, as x approaches x naught in each case, is going to be less than or equal to this limit, providing it exists. We want to show it 0. Right? But now, f of t is less than or equal to m. So this is less than or equal to the integral from x naught to x of m dt, where capital M is a bound on the function f. We know it's bounded. The integral of m dt is m times x minus x naught. Right? And this is going to go to 0 as x approaches x naught. So this limit is this limit as x approaches x naught, which is equal to 0, and that's what we wanted to show in the first place. So what we have here then is that if little f is integrable, then the capital F is continuous. The fundamental theorem is going to show us that there's one further step to this, namely that if little f is continuous, then capital F is differentiable. Capital F tends to always be just one bit better than whatever little f is. All right? Capital F is always bounded. Little f is always bounded, and capital F is always continuous. So it's always one step better. But if little f is continuous at a point, then capital F is going to be differentiable at that point. And finally, what we're going to show is that if little f is continuous on the whole interval, then capital F is an antiderivative of little f, and we can use it to evaluate the integral of little f. That's coming next. Okay. Continuing now with the fundamental theorem of calculus. Imagine we've got little f over here. Again, draw this positive for a moment on the interval from a to b. And we assume that f is integrable. And now suppose if f is continuous at a point x naught. So here's a point x naught. And what we wish to do is to show that then capital F of x, the integral from a to x of f of t with respect to t, is differentiable. At x naught, and the derivative of capital F at x naught is little f at x naught. So the function little f is continuous, then the function capital F here's f at x naught, here's capital F at x, is going to be differentiable. We're going to compute the limit again from the right for x larger than x naught. When x is less than x naught, the situation is similar. So what we want to do is the following. We want to show that the limit as x approaches x naught, f of x minus f of x naught over x minus x naught is equals to little f at x naught. Or, if you like, that this minus little f of x naught has a limit of 0. So what we really want to do is we want to look at the absolute value of this and show that it gets very small. Okay. Capital F of x is the integral from a to x of little f of t dt. And capital F of x naught is the integral from a to x naught, little f of t dt. And now I'm going to write this over x minus x naught, and I'm going to put this up here minus f of x naught times x minus x naught. Right? Now this quantity, f of x naught times x minus x naught, is equal to the integral from x naught to x of f of t dt. Why? I'm sorry, of f of x naught dt. F of x naught is just a constant. And if I integrate it from x naught to x, I'm going to get that constant times the length of the interval, x minus x naught. So that I can now rewrite this as an absolute value. This is going to be equals to, here this is the integral from a to x minus the integral from a to x naught. So it's going to be equal to the integral from x naught to x, f of t dt, minus the integral from x naught to x of f of x naught dt over x minus x naught. Right? Now this is the integral of two different functions. This is the constant function f of x naught. This is f of t. So this is going to be equal to the integral from x naught to x of f of t minus f of x naught dt over x minus x naught. Right? This, an absolute value, is going to be equal to this. It's going to be less than or equal to what you get if you put the absolute values inside here like this. Right? As before. But now what happens here? This is going to be less than or equal to, by the continuity of f, we can make f of t minus f of x naught very small, providing t is close to x naught. And it will be close to x naught if x is close to x naught. So this is going to be less than or equal to the integral from x naught to x of epsilon dt divided by x minus x naught. Right? Which of course is equals to epsilon times, this is a constant over the interval x naught to x, so x naught, x minus x naught over x minus x naught, which is equal to epsilon. So that shows that this absolute value here is less than or equal to epsilon, no matter which epsilon you choose. You can find a delta so that by the continuity this is less than epsilon, and so consequently when x is close to x naught, so consequently this limit here is equal to 0, and the derivative of capital F is little f at any point x naught where little f is continuous. Right? Now, one more result coming up is going to be then, all right, if little f is continuous on the whole interval, then the integral is differentiable on the whole interval, and the value of the, if you take any antiderivative of little f, you can evaluate the integral of little f by taking the difference between the value of the antiderivative at the right-hand endpoint and the value of the antiderivative at the left-hand endpoint. Okay. Now, if little f of x is continuous on the interval AB, then capital F of x, integral from a to x of f of t dt, is differentiable. On a to b. Now, actually what's being asserted here, but is not going to be proved at this point, is that if little f is continuous, then it is also integrable. So that continuous functions are always integrable, and moreover, their integral is an antiderivative. Because what we must also have is that f prime of x is little f of x from the previous result at each x in AB. Now, moreover, if g of x is any antiderivative of little f of x, then the integral from a to b of f of x with respect to x is g of b minus the value of g at a. All right. So continuous functions are integrable. All right. That's because you can get the upper sums and the lower sums, or all the sums, to differ by as little as you wish because of the continuity. But that takes considerable proof. Continuous functions are integrable, and the function capital F of x for a continuous function little f is differentiable, and its derivative is little f on the entire interval. And now, if g is any antiderivative, then you can evaluate or determine the value of the integral from a to b by taking the value of g at b and subtracting the value of g at a. This last part is real simple. Let's suppose g an antiderivative of f. Then what? If we look at the integral from a to b of f of x with respect to x, this is equal to f of b, where f is the integral from a to x. But it's also equal to f of b minus f of a, because f of a is 0. The integral from a to a is 0. G is an antiderivative of f, and f is also an antiderivative of f. That's to say, the derivative of capital F is little f. So that f of x and g of x differ by a constant. F of x is g of x plus c. So that consequently, f of b minus f of a is equal to g of b plus c minus g of a plus c, which is equal to g of b minus g of a. But f of b minus f of a was the integral from a to b of f of x with respect to x. So we now have the integral from a to b of f of x with respect to x is g of b minus g of a. So in order to find the integral of a function, what we're going to want to do is just find any antiderivative g. We don't have to worry about the constants. Take the value at b and subtract the value at a. And we will generally write this as g of x evaluated from a to b. This is a good preliminary step here. When you find the antiderivative, write it, put a and b here, and then note that that means to take the value at b and to subtract the value at a. So that then is, at least in outline form, the fundamental theorem of calculus. Look at some examples here then and see how much easier this becomes when you know how to find the antiderivative of a function. Let's suppose we wanted to know the area underneath the graph of, let's say y equals x cubed between, let's say, 1 and 2. I want to know this area here. Well, this is going to be the integral from 1 to 2 of x cubed with respect to x. And antiderivative of x cubed is x to the 4th over 4. We don't need to put the constant of anti-differentiation here because we're going to evaluate this then from 1 to 2. That's to say we're going to take the value at 2 and subtract the value at 1. In doing this, especially if whatever is here is complicated, it's a good idea to give yourself two parentheses with a minus sign in between them and put then the value at 2 here, which is going to be 2 to the 4th over 4, and subtract the value at 1 here, which is 1 over 4. So this is equals to 16 over 4 minus 1 over 4, which is equals to 3 3/4, or 15 quarters. So the area underneath here is 15 quarters. At this point, I just want to take a look at evaluating definite integrals here by finding the antiderivatives. So that, for example, if you had something like the integral from 0 to 5 of x squared plus 7x plus 10 with respect to x, right? Without concerning yourself with the interpretation of this, you can simply find an antiderivative of this. It's x cubed over 3 plus 7x squared over 2 plus 10. You want to evaluate this from 0 to 5. That's to say you take the value at 5 and subtract the value at 0. The value at 0 is 10. Right? The value at 5 is 125 over 3 plus 7 times 25 over 2 plus 10. This should be 10x. So this is 10 times 5. So plus 50. So you find an antiderivative, x cubed over 3 plus 7x squared over 2 plus 10x. Take the value at 5, subtract the value at 0, and the value at 0 here in this case is 0. And this then will tell you what the value of this integral is. Namely, it's that number right there. If we wanted to know, let's say, the integral from 0 to pi of, or let's say, pi over 2 of cosine x. Right? Here, the interpretation is simple. If here's cosine x between 0 and pi over 2, it's this area right here. Right? Antiderivative of cosine x is sine x. We want to evaluate it from 0 to pi over 2. So we want to take the value at pi over 2 and subtract the value at 0. The value of sine at 0 is 0. The value at pi over 2 of the sine function is 1. So that the area underneath the cosine function over here is 1. Okay. Let's suppose we want to find the area between the function 8 minus x squared and the x-axis. 8 minus x squared looks like this. It's a parabola opening down. Its the maximum is at 8. This is 8 minus x squared. In order to do this, we need to find out what the limits of integration here are. 8 minus x squared is equal to 0. When x is equals to minus the square root of 8 and the square root of 8. So to find this area here, we would want to integrate 8 minus x squared with respect to x from minus the square root of 8 to the square root of 8. And the antiderivative now is going to be 8x minus x cubed over 3. We want to evaluate that from minus the square root of 8 to the square root of 8. That's to say we take the value at the square root of 8 and subtract the value at minus the square root of 8. It's going to give us twice the value at the square root of 8. Clearly here by the symmetry, if you want. And so that this is going to be equals to 8 square root of 8 minus the square root of 8 cubed over 3. All right? So you can, if you've got a particular curve here and you want to find out what the area underneath the curve and above the x-axis, you can do that by finding what the limits of integration are.